episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. Just like everyone else on this planet, I am not perfect, not in life, nor as a developer. But that doesn't make me unique in the slightest, since nobody is perfect and no developer is perfect. However, with that being said, in software development, sometimes our mistakes, for lack of a better word, actually end up working, and because they work, they often go untouched or unnoticed because of, the age-old saying, if it ain't broke, don't fix it. Now, these mistakes, as I called it, that also end up working, are something known as anti-patterns, or solutions to problems that hurt the code's overall either readability, maintainability, reusability, or other things of that nature. So today I thought we would take a look at some of those which I myself have been guilty of in the past, and I'm sure almost every developer has been at some point, and talk about, one, how they happen, but also how you can kind of identify them and prevent them from happening in the first place. So that is coming up in this week's episode, but before we get into that, let's start off with our trivia question. So, which protocol is used to send emails over the internet? So, what is the protocol that is used to send emails over the internet? And that is your trivia question for the week. Now, I guess one quick thing on that trivia question, if you give me either the acronym or what the acronym stands for, I will accept both as the answer. Now, last week, our cybersecurity tip wasn't exactly for us normal people and was for hotels due to their egregious nature of not seeming to care about who people say they are when asking for keys and various things related to their room. But this week, we are back to our regularly scheduled programming finally. So with that being said, let's get into this week's cybersecurity tip. This week's cybersecurity tip is probably going to make me sound like a broken record, but it is to be mindful of senders of emails as well as links in emails. Now, I know this has been a tip in the past, at least on several different occasions, but I don't know about you guys, but I have definitely noticed an uptick in very convincing looking emails from reputable companies that in reality are just phishing emails. And recently, CrowdStrike, that company, I think it was back in July, that basically blew up the internet. Yeah, them. They noticed a phishing attack campaign targeting job seekers that would actually download and run the XMRig crypto miner. And one of the reasons they noticed this was because the phishing attack actually was meant to appear like a CrowdStrike email being sent to, I believe it was like junior developers or something, basically telling them to like download this app or whatever in order to, do whatever the next phase of the application is. I don't know. But anyway, it's a classic phishing attack where essentially the email looks exactly like a CrowdStrike email with the same logos, fonts, headers, footers, all that good stuff, and basically looks like an official CrowdStrike email actually would. And like I kind of mentioned at the beginning of this tip, I've noticed that from multiple different companies at this point within the past month. I've gotten, I think, a couple from Apple, well, allegedly from Apple, that look very much like an Apple, email for something to do with either an Apple purchase or an account, information or things like that. I've gotten things from Coinbase and a couple other different companies that look very much legit, but of course, under a little bit further inspection, the facade fails dramatically because the email is completely wrong, and then of course the links, which I don't click but I copy and then paste into like a text file or something just to see what they are, have absolutely nothing to do with the alleged company that is allegedly telling me there is either an issue with my account or whatever the case may be. Now, like all solutions for phishing emails, basically, like I touched on there, the number one giveaway to tell that an email is a phishing email is to, one, inspect the links in the email. Of course, don't actually click on them, but you can either copy them and paste them into a text file or something like that to inspect them, and also verify the email address from whoever the sender is. Make sure the domain that it's coming from is actually from the company that they're claiming to be from. Those are some two very big giveaways that you have a phishing email on your hands. And depending on the context of the phishing email, if it's something to do with like an issue with your account or something like that, and you really want to be on the safe side, my go-to recommendation is and always has been go directly to that site's page. Don't use any of the links in the email. Go directly to that site's page and log in with your credentials. And if there actually truly is an issue with your account, it should be plain as day as soon as you log in. And if it's not, you either, one, don't actually have an issue with your account and it's a total phishing email, or two, if you're still not convinced and you still think there might be an issue with your account, once you log in, somewhere in there should be like a phone number or a customer support line that you can contact and, confirm with them directly if there actually is an issue with your account or whatever the case may be. Now, in a statement, CrowdStrike said, quote, "Victims are prompted to download and run a fake application which serves as a downloader for the crypto miner XM Rig." Now, essentially what this phishing email is doing, kind of like I touched on, is it basically lures in the recipients claiming they've been like shortlisted for like the next stage of the hiring process or whatever, and then they need to download this link in order to join a call with the recruitment team in order to, I guess, continue on with the next part of the process. And of course, in that link that they're told to click to download, the tool or whatever is actually the malware being downloaded. And of course, the cherry on top of this is once the malware is downloaded, it covertly, pulls down the XM Rig miner and starts mining in the background. But then on top of that, it also collects a bunch of, identifiable information about the system, like the public IP address, system metadata, process lists, directory lists, IP addresses on the network adapters, installed applications, all of that fun stuff that you probably don't want a piece of malware knowing about you and your network. And it's interesting because this also comes on the heels of Trend Micro's reveal that there was a fake proof of concept for a recently disclosed security flaw in Microsoft's LDAP, or Lightweight Directory Access Protocol, that ended up luring actual cybersecurity researchers into downloading this fake proof of concept, which actually ended up being an information stealer. So even the best cybersecurity professionals can be fooled by some of these things. And if you're wondering, why there would be a proof of concept made, the main reason why, cybersecurity researchers make these proof of concepts is just to show that, yes, this is actually a vulnerability, or yes, this is actually an issue, and here is just a basic example showing you how it works and showing you how you can exploit it and getting the system to do whatever you want. In some cases, that's remote code execution, or that's a reverse shell, or, whatever the case may be. So yeah, when it comes to emails, always be sure you are verifying any links in them before you click on them, and you're also verifying the sender in order to make sure they are actually legitimate and not phishing. And that is your cybersecurity tip for the week. So let's move right on into what nerdy stuff have I been up to this week. So this week, I am no stranger to trying to make my own operating system. I've tried a couple of different occasions. The first one, I took an operating systems class back in college, and we basically wrote the initial stages of a kernel. Basically, all it did was it used the grub bootloader, and then we wrote a kernel that just basically printed hello world to the screen, and that was basically it. It didn't do anything else. And then after that class, I kind of took it upon myself to add a little more, I guess, features, if you will, a little more capability looking through tutorials and everything. Wrote some really ugly and terrible code and hacked a few features in there. Again, nothing was very clean or elegant about it. It was a hack job, basically the definition of a hack job. But it did kind of work. You could enter in keyboard commands, sort of. I mean, the keyboard kind of worked. You could only enter capital letters, though. And I think the only actual commands it recognized was like clear, and there was a spoof login type thing that had hard-coded credentials in it. Yeah, it wasn't, really the best, but, you got to start somewhere, right? And then more recently, I've talked about it on the podcast before, is I followed a tutorial by Nanobyte, I believe it was Nanobyte on YouTube, about making my own operating system from scratch, and that worked pretty good. I got, the bootloader and everything and the kernel working, and then kind of hacked together a keyboard driver, and this keyboard driver actually allows you to write not only uppercase but also lowercase letters and special characters and all that fancy goodness. So that was pretty cool. But aside from that, it didn't really do anything. But the most recent attempt wasn't actually starting from scratch this time, and instead I decided to try to create my own Linux distribution. Now, we need to take a step back because this is not something that I started this week. Quite the contrary, actually. I honestly don't remember when I started this, but it was probably months ago. But the reason why I held off mentioning it at all on the podcast was for a couple reasons. One, it didn't really get all that far. I mean, I got some basics of it working, but I also had other things to talk about, so it wasn't all that high on the priority list. Because as you'll see as I walk through kind of the various iterations of it, it didn't end up doing what I wanted it to do until basically yesterday as of the recording of this podcast. So starting from the beginning, which, like I said, I don't remember when it was, but a few months ago, the first iteration was, of course, building the Linux kernel from source. That's kind of step one. So that wasn't too difficult to do. And then after I got the kernel built, it became the process of getting it to actually boot and being able to boot into the Linux kernel. Then after that, it became the process of, okay, you have the kernel booted, but now you can't do anything. So after that, I had to figure out how to get the various Unix utilities included in the operating system. So I ended up going with the tried and true BusyBox, which from the research I did is a pretty common solution for the Unix utilities. So it gives you access to commands like grep, cat, cd, all those good commands that you're used to using from the command line. So I got that working. And then the next thing I wanted to do was I wanted to include my own programs into the operating system. Now, there's a couple different ways you can do this. I started off with the, I guess, more simple and straightforward way, which was statically linking everything. And essentially what that means is your program doesn't rely on any libraries whatsoever. So when it comes to compile time to build your application, anything that you normally would use a library for, like for example, if you're writing a C program, printf, typically you use the libc library in order to make that printf call. But if you're statically linking everything, that code for printf is then included within the binary of your program. So the nice thing about statically linked binaries is you don't have to worry about any kind of dependency issues because all the code that the program needs to run is included directly in the executable itself. The downside, of course, is the file sizes for statically linked applications is significantly larger because, of course, there's a lot of extra code that typically is, in a shared library somewhere that has to now be included inside of your binary. But this was the kind of first iteration to kind of getting my feet wet in getting my own programs into the operating system. And it did work, and it worked pretty well. But the next stage came to I wanted to dynamically link things. And the only way I could do that is to somehow get glibc in there. So I guess you can probably see where this is going. I decided to compile glibc from source and include it inside of the operating system. And then, of course, I ended up bricking things on multiple different occasions because once I started adding glibc, I was like, well, there's no point in trying to statically, include all the libraries for BusyBox because glibc is going to be there, so I won't have to worry about statically linking things. And that caused many a kernel panic because when I was installing glibc, like inside of the temporary operating system directory before I kind of zipped everything up into the ISO image, was the library directory that glibc was putting files into was not the directory that BusyBox was looking for. So I had to do some kind of finagling around to get that working, but I did eventually get both BusyBox and my own programs included in the operating system as well as dynamically linking with glibc, and all that was hunky-dory. But the next problem came where I wanted to actually be able to do something with this operating system. And I guess, sure, I could, run my own programs that I included, but where's the fun in that? I mean, you can't actually do anything with it. So what I decided to do, which ended up being the biggest hurdle that took me the majority of the time, I think, that I was trying to work on this, was having the ability to write my own programs in the operating system. Now, sure, I could have used a scripting language like Bash or something that's already pre-included and supported, but I wanted to write programs like C programs. So in order to do that, I needed GCC. And boy, oh boy, was trying to get GCC to work an absolute nightmare. And I'll tell you what, jumping ahead to the future in this story timeline, when I finally actually got GCC working, I honestly didn't believe it because everything I had tried up to that point didn't work, even when there were some times I was like, okay, for sure it's going to work this time, and then it didn't work. So I kind of got to the point where I expected that it just wasn't going to work no matter what I tried. So then when it actually worked, I was quite astonished and kind of had to do a double take. But anyway, back to the present in this timeline, I decided I wanted to get GCC working. And actually building and compiling GCC, in all reality, was the easy part. It was everything that comes after that caused many headaches. So the first issue I ran into was trying to actually include GCC into the operating system. So up until this point, I was essentially using the init ramfs, which essentially is the initial file system that's used in order to transition the Linux operating system over to the main file system. And every time I was trying to include GCC in this init ramfs, it was kernel panicking every time and just basically blowing up. And it was not a fun time. So After a lot of troubleshooting and researching, I found out the reason for this was the init ramfs was too large, surprise, surprise, and it was unable to be properly loaded, at the boot process, so it was causing the kernel panic. So then I had to figure out how to create a kind of an additional temporary file system for the actual operating system in order to include my own programs as well as GCC and anything else I wanted to include that wasn't strictly needed for the actual boot process in order to change the root of the file system over to the new file system that has all the programs and the goodies that I want. So that took quite a bit of time to figure out. But once I got all that sorted and it wasn't kernel panicking anymore, then came the nightmare of dependencies. And if you've ever tried to build your own projects from source, you've probably ran into this issue before, where you are missing dependencies for the project and thus it's not able to run, or certain parts of it don't perform as expected. Now, today we kind of take dependencies for granted because especially if you're on like a Linux system, whether that's like Ubuntu or Fedora or Arch or any one of the major Linux distributions, they have what's known as a package manager. And the package managers have come a long way to the point where if you want to install an application, like if you want to install GCC in order to be able to build and compile your own programs, basically everything that's required for GCC to run, the package manager is smart enough to understand what's needed for it to run, and any packages that you didn't explicitly list, it'll go ahead and pull those down and install those for you so you can run the program as it's expected. But when you're building everything from source and you don't have a package manager, you have to kind of figure all that out on your own. So at first, it started out with first off, the first issue was pretty trivial, and that was a pathing issue. So the system was looking for the GCC executables, and it wasn't able to find them, so that was an easy update to the path, and done deal. The next problem was it couldn't find certain libraries. So GCC relies on a couple of various libraries in order for it to work properly. Now, this took me way too long. It took me a lot longer than it should have because I ended up just being a dummy and didn't run the included download prerequisite script that's included with the GCC source code. If I would have done that, a lot of these library issues would have been completely avoided, but I, of course, did not read the documentation. Don't do what I do. But then after that, after that embarrassingly long amount of time, came the next problem where GCC was looking for a couple different executables that were not present, and those were found in the bin utils, which was not included in the operating system I was building. So I had to go out, grab those, compile those from source, and include them in the operating system. Then, once I got all that squared away, I was finally able to compile and run a program inside of the OS. And like I said, I had to do a double take because it was so incredible to see everything finally work as it was supposed to. And then once I got everything working, I decided to do what any good developer would do and immediately break it. And I didn't do it intentionally, but the first thing I did that I thought might break it was I actually cleaned up the build environment, because up until that point, a lot of the testing I was doing, I wasn't really cleaning things up after each run, mainly because I don't know. I guess part of it was I just kind of wanted things to go faster, even though they really didn't, because I was just running a script over and over again to do all this for me. But the reason I actually broke it was I was trying to do some fancier stuff in the init script. So like when the operating system, when the kernel loads, you have to set some kind of function to be the init function, so the kernel can actually do something. So there was an issue in my init script which caused the OS to kernel panic. So I was like, oh no, I broke it. It was literally just working, and now I broke it. So that took a little bit of troubleshooting, but that was a pretty quick fix. But then once I got that figured out, cleaned everything multiple times and reran things just kind of as a sanity check, just to make sure things were working repeatably and actually doing what they were supposed to do. And in fact, they did. So then once I kind of got that squared away, I started, kind of dividing up the script, because of course I was not doing any of this by hand, because that would be way too much effort and attention needed, because running this script, especially if you're including GCC, of course, it depends on what computer you're using, but at least with the computer that I was using, it was taking, I think, roughly like maybe 15-ish minutes to actually build everything and create the ISO image in order that you could then boot from. So yeah, it was it's quite the process. So actually having to do some manual intervention there to run commands would be an absolute nightmare. So of course the only solution would be to make a script out of it. But the script that I originally was using was pretty terrible. It was because everything was just in one script, which, don't get me wrong, it worked, but it wasn't very modular at all. So after I got everything working and verified things were working, I then kind of started splitting up each of the individual components and putting them into their own scripts. Like, I already had like comments and things kind of dividing up the various sections of the script, but everything was just in one script. So I ended up kind of pulling out those sections and putting them into their own scripts, and then in the main script kind of just calling the individual scripts. And the nice thing about this is, because I'm making things more modular, it allows me to, like, if I only say want to recompile the kernel but don't want to rebuild all of the other pieces of it, I can just run the part of the script that rebuilds the kernel and then run the scripts that create the ISO image without having to rebuild everything else. Now, granted, that could potentially pose an issue with some of the other pieces that rely on headers from the Linux kernel, so that was probably a bad example. But say, for instance, if I wanted to update GCC to a newer version, I could just run that script to update that, or run the script that builds the programs that I want to include in the operating system, just rerun those, and then run the scripts to build the ISO image, things like that. The modularity is definitely very nice to have. Now, I do plan to publish all of this work to GitHub, on my GitHub at some point, but I wanted to kind of clean things up a little bit more, because, like I said, I literally just got this working yesterday as of the day I'm recording this. So I want to, take some time to clean up some of these scripts, and there are still a few pieces I want to kind of take out and modularize. But one thing that I will say I do like about my script, I know there's a couple different versions out there on GitHub that essentially do the same thing. There's basically just a single shell script, or sometimes a collection of shell scripts, that'll build a very basic primitive Linux operating system for you, which I didn't really know existed until I was kind of really already deep into the weeds with this. Yeah, but the one thing I like about mine over some of the other ones is, some of the other ones I've seen, they basically ask you which versions of the various things you want, like which version of the Linux kernel you want, which version of BusyBox do you want, things like that. And then it'll go out and basically pull down like the archived version that you want, extract it, and then build that, which that's definitely a valid use case. But what I ended up doing, which I guess you can, if you don't think it's the better solution, you're more than welcome to have that opinion. But the solution that I went with was to essentially clone the repos, like the source repos themselves, and then basically whatever version you want to run, just do a git checkout of whatever tag you want to use, and then it can swap. You can easily swap between versions like on the fly rather than having to go re-download the new version and all that good stuff. So this kind of allows you to either be on the absolute bleeding edge and just taking whatever's in the master branch at that time, or being able to check out to the latest stable release. You kind of get that flexibility. So I do want to emphasize, though, I didn't just knock all this out recently. Like, this was something that I've been tinkering with on and off for a few months at this point. Because like I said, I don't remember when I started, but it also wasn't a process that I was doing frequently because, as you probably remember from the past few months, I never brought this up once in any of the nerdy things segments I talked about because I was doing other things as well. So this was definitely very much one of those things that I just kind of would, if I was bored or something, I would go kind of tinker with a little bit, try and experiment with a couple things, and then inevitably things would continue to not work. So then I'd be like, okay, I'm done with this for now. I'm going to go off and do other things, and then I'd come back to it like a few days later and just tinker with it a little more. But yeah, also, I guess this begs the question, maybe some of you were wondering, no, I will not be switching to this OS as my daily for a couple of reasons. One, as I touched on, there's no package manager or any way to update it, meaning if I ever wanted to update anything like the kernel or BusyBox or glibc or GCC or anything like that, I would essentially have to manually rebuild the operating system from scratch, which I don't particularly want to do. And the other issue is because the operating system doesn't install itself, it's literally just like a live image. There is a small amount of space on the image that you can write, files to, but nothing gets saved. So as soon as you shut down the system, whether that's in a virtual machine or if you're using real hardware, all your data's gone. So it doesn't really make for a good daily operating system since you can't really save anything. And I haven't tested out internet or anything like that. But there's also no tools like SSH or a web browser or any kind of office tools or really anything that you would need for a daily driver operating system. Now, granted, I guess if I wanted any of those tools, I basically just have to add it as part of the build script and compile everything from source, which I definitely could do. But this was, more so one of those kind of hobby projects to kind of really more understand, what goes into kind of building an operating system from kind of a high level perspective. Obviously not going deep into the weeds, like how do you, program the various drivers and interfaces for CPUs and interrupts and all that good stuff that goes into the kernel, but just kind of the high level of what goes into and comprises an operating system. Once you actually boot into the operating system, how do you kind of transition into the main file system from kind of the initial one, things like that. So another thing I'd also like to add before I publish things is some kind of script or something to check for and install dependencies, because right now in the main script, because I've been just testing on a single system that I already got all the dependencies installed for, there's just a kind of a note there that says yeah, by the way, this just kind of assumes you have everything installed. Which of course is not ideal. Ideally, I'd like to either have a script or somewhere to define all the various packages and dependencies that you need installed on your host system that you're going to be building this operating system on, so you can actually install those and be actually able to run the scripts, rather than doing a bunch of guesswork of trying to figure out everything that you need by a bunch of trial and error of trying to run the script, realizing something doesn't work, and then going installing packages and then trying again and all that. So at some point I do kind of want to try to consolidate what all the individual components are that you needed to build the system. But yeah, that was what I wanted to talk about this week for the nerdy things. This was kind of a long time coming, like I said, but I did kind of want to finally bring that to the forefront. So I guess now we should probably get into the kind of the main topic of this episode, which is this idea of anti-patterns. So kind of like I touched on in the top of the episode, anti-patterns are commonly recurring solutions to problems that are counterproductive or ineffective. And of course, when I say solutions, that's kind of in air quotes because, in other words, anti-patterns are just common mistakes or poor practices when writing code. So to highlight and kind of get an understanding of why anti-patterns are bad and why you should avoid them for writing better, scalable, maintainable, and robust software, we're kind of gonna get into that and why some of these anti-patterns are counterproductive for those types of things. So the five that I wanted to touch on is, the first one is the God object, spaghetti code, cult programming, premature optimization, and finally, not invented here syndrome. So I guess starting off with the first one, known as the God object. So this is a class or object that does way too many things and basically violates the idea of a single responsibility and modularity, basically takes those ideas and throws them out the window. So some common symptoms of this is you have massive files or classes that have more than one responsibility, or you have multiple kind of coupling components kind of like all roped into one object. So the reason why this is a anti-pattern and bad is because, well, yes, it works, it overcomplicates things and can make things a lot more difficult to understand and modify, because if you have a single class or object that does multiple things, it's hard to come up with a good naming scheme for what the class should be if it's doing multiple things, if that makes any sense. So because of this, it increases the risk of bugs due to unintended side effects, because if you're trying to have one class do multiple things, you might have one portion of the things it's doing working pretty good, but then because you change something somewhere, it could affect someplace else. So kind of an example of this is, let's say you're kind of working with some kind of user interaction system, whether you're having a website where users have to log in, or you have some other kind of user management system as part of your project. If you had a single user management class that handled the authentication, user profiles, database operations, and notifications, I think you can kind of see why that one class should not be doing all of those things. Now, yes, technically, all of that stuff is part of user management, because you're going to have to somehow authenticate them. A user's going to have a profile. The user, whenever they need to, access things, is going to have to do database operations. And then, whenever the user gets notifications, they're going to have to receive those. But each one of those different pieces should be its own component. And that makes, kind of understanding and managing the code a lot simpler, because you can divide all of those individual pieces up into different classes and different objects, and into different files, and make things a lot more maintainable, readable, and understandable. And you don't have to worry about trying to comb through, thousands of lines of code in a single file just to find that one function that you were looking for. That is a completely different component from the one you were previously working on. So having a massive class like this definitely hinders the reusability, because if you want to use this object or class in the future, you're basically, and you only want to use one of those components of it, you're bringing all this extra baggage along with you that you don't actually need, and bringing in a bunch of dead code that you're not going to use, and it's just not a good practice. So The solution to this is to, one, refactor things and make things smaller into more well-defined classes and kind of adhering to that single responsibility principle, where essentially, rather than having a single class that handles the authentication, user profiles, database operations, and notifications, each one of those components is its own class and has just its own singular responsibility. So that is kind of the God object and why you want to avoid those. But I mean, as you can see, though, just looking at that, I mean, if the class does all of those things and it works, you could see why that is technically a solution, even though it's not a very good one, especially in terms of, trying to scale the program up, maintain it long term, and all that good stuff. The next one is one I'm sure most people that have done any kind of software development are familiar with, and that is spaghetti code, which the funny thing about spaghetti code is not too long ago, I think it was actually this past week, I saw a meme that was a picture of it was posted, I think, on like a programmer humor like subreddit or something. But essentially what the picture was someone had like a bowl of spaghetti on the table, and someone was like, "Oh no, I dropped my code all over the table," or something like that, which I thought was pretty funny. But anyway, spaghetti code, if you're not familiar with the term or don't know what it is it's code with very little structure or organization, resulting in a very tangled and unreadable mess. Now, anyone that has ever written software before has either, one, written spaghetti code or has had to deal with spaghetti code. And let me tell you, it is not fun to deal with. And some kind of the major symptoms of spaghetti code is modularity is generally pretty poor, and it's kind of hard to understand the flow of the code, like as you're trying to read it. Another thing that's pretty common when it comes to spaghetti code is a lot of kind of global variables, as well as kind of hard-coded values or the glorious magic numbers. Because one thing that is very annoying when reading through code is seeing magical numbers or hard-coded values just in the code with no real reason of why they're there. I mean, even when a comment's there, I mean, that's helpful, but at the same time, it's not necessarily the best solution either, because depending on what that magic value is, if you change it in one place and it's sprinkled throughout the code, it doesn't get updated everywhere. And it's a royal mess trying to track down every place where that magic number was placed in order to update them all. But not every time that number is somewhere is actually it being referred to as the magic number, and you're probably starting to see how this code is very much spaghettified at this point, because you're going all around Kingdom Come trying to go through all the various classes, trying to decipher what actually matters and needs to be updated if you're trying to, make it more maintainable and reusable with actual variables. And it's just extremely difficult to debug and maintain, and the time cost to both, troubleshoot and debug and make updates and do bug fixes is significantly higher when your code is very spaghettified. And I know from a kind of a managerial perspective, it's kind of hard to justify I guess it depends on, the industry you're in and whatnot, but it can sometimes be pretty hard to justify refactoring spaghetti code to management for a couple of reasons. One, management, especially if they don't have any kind of software development background, they'll be like, okay, so let me get this straight. You want to do code writing for, say, 4 months, but at the end of it, there's going to be no difference in how the code operates. Why the heck would I do that? Which is, in all honesty, a very naive way of thinking, because the thing that they often don't understand is, while yes, you're basically quote unquote throwing away however many months of work that is. But at the same time, if you do it right, rather than it taking, say, 2 months to crank out a new feature, you can crank out that new feature in, say, 2 weeks. So you can, iterate a lot quicker and make updates a lot quicker, fix bugs a lot quicker, and the overall, cost to do updates, do bug fixes, things like that is significantly less than if everything was spaghettified. But the problem is when you have spaghetti code, someone somewhere has to spend the time to go through and refactor all of that code to unspaghettify it, which takes, depending on how big the code base is, a very long time, a lot of energy, and a lot of dollars that, generally speaking, people don't like to spend because from their perspective, you're not actually adding anything to the code. The code still, at the end of the day, before you untangled all the spaghetti, it did X, and then after you untangled the spaghetti, it still does X, and from their perspective, nothing has changed, so you basically just wasted all of that time, which obviously is not true, but that is generally how it's kind of viewed. So, of course, the solution to avoid spaghetti code is to adopt modular programming techniques, things like object-oriented programming, doing things like code reviews and having code standards to make sure that, people aren't using those magic values, they're using variables, and using other kinds of frameworks or libraries to enforce structure and things like that, just to ensure that things aren't kind of going all up around everywhere and all kind of spaghettified. So the next one is probably one that I think a lot of people also have fallen for, which is kind of this idea of cult programming, or in other words, blindly following patterns, practices, or code without understanding their purpose. Now, what I'm not saying here is, not following a style guide, because following a style guide is definitely something that is very important and something you should be doing because it helps the readability of the code a lot easier. Because if all of the code throughout the project is the same, all the formatting is the same, it's a lot easier to read and things aren't jarring and don't jump out and kind of distract you from trying to read and understand the code. The other nice thing of it too is it helps to kind of prevent the idea. It makes it all look uniform, like it wasn't written by, 20 different developers working on the project. It all kind of looks like one seamless thing. So when we're talking about cult programming, we're not talking about, following a style guide. What we're talking about is, say you're trying to work on a new feature or a new function, and you're referring to a similar function that happened to use a linked list to solve its problem, so you just automatically take that code and paste it into your function, make the minor tweaks, and then just call it a day without really considering of A, should I actually be using a linked list here? Or B, is this even the best solution, or are there better alternatives? Essentially just blindly copying without, considering alternatives. Or, as I think most people have probably done, the good old Control-C and Control-V from Stack Overflow, and things all of a sudden decide to work and you pay no extra attention to why they work. That's kind of what we're talking about here. So some issues that kind of crop up with cult programming is, say you fell into one of the other kind of issues on this list, or you kind of over-engineered a solution for something, or misused design patterns or something like that, and now that code is being copied all around the code base blindly and not really doing anyone any favors and kind of harming the overall readability and reusability of the code. And depending on what's being copied, it could potentially create potential vulnerabilities in the code base because, for instance, say let's go with a hypothetical here. Say someone in one function, they set a static buffer size and then copied some data into it and then continued about their day. Now, from their perspective for their function, doing that was fine because the data coming into that function was guaranteed to be a certain length that that buffer was set to. However, in the function that you copied it into, there is no guarantee of the length of the data coming in, so then you just blindly copy that data into that buffer, and oops, you got a buffer overflow. So this is kind of one of the issues with kind of cult programming and why it can definitely be a huge issue, and why you shouldn't just be blindly copying code, but rather if you are copying code, you should be really taking the time to understand what that code is doing and if that actually is a good use for whatever you're trying to use it for, aside from its initial intention. And the other kind of issue with cult programming too is one, if you just blindly copying code around, you don't really understand what it does or why it works, and that is one of the most important components of being a good software developer. But also it kind of limits your innovation too, because if you're used to, just copying your answers from somewhere else, you don't really gain those problem-solving skills to come up with the solutions on your own, which is not very good. You want to be able to kind of come up with those solutions on your own. I mean, now granted, as we'll see, on the fifth one, which is, essentially not reinventing the wheel, granted, you don't want to reinvent the wheel, but you also, want to be able to, come up with and solve problems on your own as well. You don't want to be dependent on other people giving you all of your solutions. So some of the kind of solutions to fix cult programming is to focus on the why. Understand why a certain pattern or practice is being applied in a certain scenario. And, understanding and trying to gather, are they using best practices, and just really understanding the why. Why was this code written this way? Why was this data structure used? Why are they using this algorithm rather than that one? And kind of asking yourself those questions can help you better understand the code for that particular use case, but also help you better apply it to the use case you're trying to use it for. So the next one I wanted to touch on is premature optimization, or in other words, optimizing code too early, either before you've really identified if there are any performance bottlenecks, and just trying to focus on the optimization piece before you've really solved the problem. Now, you guys probably know that I love optimization. I've done numerous segments on this podcast specifically talking about optimization. One time I even talked about, cache optimization and how, depending on how you do your for loops, you can see 40 times gains in performance just by, this one little trick, the clickbait version. But my primary goal whenever I write any kind of code or try to solve a problem for the first time is make sure that the solution I come up with actually works. I don't really care about optimization. Now, depending on the problem, if I've encountered a similar problem before and know that, I can do it going through, say, a for loop once rather than a nested for loop, sure, I'll, start off with that basic background of going, through a single for loop rather than a nested one. But I'm not, focusing on trying to optimize and squeeze out every bit of performance before I know my solution actually works. Because in my experience, I often find that when I try to optimize too early, I end up, one, overcomplicating things and making things way harder than they need to be. And two, I often run into a lot of self-imposed mental roadblocks along the way while trying to figure out what the actual solution is, because I'll be going down a path and then think to myself, no, that's not very optimal. I'm not going to think about that. I'm going to try to figure out how to do it more optimally. And then basically just, put myself in a ditch essentially because I'm trying to solve two problems at once rather than first figuring out an actual solution, then figuring out how to do it more optimally. Because the nice thing about doing it that way, of kind of breaking it up into those two steps, is once you have a solution that works, you then have a baseline that you can compare your optimizations to. Because if you think trying to do optimizations first and you're like, okay, I'm just going to focus on trying to optimize this solution, if you're only focused on that, one, you might potentially miss some edge cases, but more specifically, if you don't have kind of a baseline, you don't really know how much your optimizations actually, improved things, right? And this is kind of goes back to that kind of initial definition of you haven't really identified if there even are any performance bottlenecks in the system at all. So you really have to kind of take those baby steps of make sure you have a solution that actually works. Then once you have a solution that works, then figure out how you can do it in a more optimal manner. And this is honestly why I really dislike platforms like LeetCode and other similar ones, because since depending on the LeetCode problem and your solution, sometimes your code will fail because it failed to meet some arbitrary time frame of when it should have been completed by, and your test case fails. Now, granted, most of those test cases are, intentionally meant to be very big to make sure your program is semi-optimal. But the problem is, it's hard to verify that your code is actually getting the correct answer when LeetCode or whatever similar platform is telling you failed because you didn't meet some arbitrary time limit. So it's hard to, verify my underlying logic is sound and correct, and I'm not missing an edge case when I'm being arbitrarily failed because I'm not doing it in some required time limit that it's self-imposed. Now, of course, when it comes to actual production code, that actually might be a serious concern that you do need to ensure your program is, or your algorithm or whatever, is meeting certain, performance metrics and being able to complete in set amounts of time. But that's the end goal, right? That's not the first step. The first step, of course, is making sure your code actually works, because you could have the most optimized code in the world that runs in O of 1 time, it's instantaneous, but if it doesn't work half the time, it's basically no good. You need to make sure your code actually works, and then you can go ahead and focus on trying to optimize it and, improving the computation time or doing things in a more optimal manner. Maybe you do kind of a sliding window approach rather than doing a nested for loop. But when you're first trying to solve the problem, to make sure you understand it, you do the nested for loop because that's what you understand, and you can gain a better understanding of what you need to account for as far as edge cases, and just simplify the problem before you start adding the unneeded complexity of optimization into the mix. So because, some of the symptoms of this, kind of like as I touched on in my own experience, when you're trying to optimize from the get-go without making sure you actually have a valid solution, is you tend to overcomplicate things and prioritize efficiency over readability and maintainability. And sometimes you're trying to optimize a specific use case or a specific edge case that might be super rarely used, and you might be wasting essentially a bunch of time on, some kind of case that rarely actually comes up in, a production scenario. So kind of some of the obvious consequences of this is wasted development time and resources, and that kind of comes back to the anecdotal evidence that I provided you of, when I'm trying to optimize and solve the problem at the same time, I'm wasting a lot of time starting to go down avenues and then thinking, no, that's not a very optimal way to do it. Let me, take a step back and try to go down some other avenue. When in reality, if I just kept going down that first option, I would have come up with a solution, albeit maybe not the most optimal. And the next thing, of course, kind of coming up in here is maintainability and increased risk of bugs. Because if you're focusing specifically on the optimization piece first, the likelihood that you're gonna, put a bug in there or miss an edge case or something is a lot higher than if you first verify your solution is working and, passing all the test cases before you then go ahead and you kind of set that baseline before you go ahead and start optimizing things. So essentially kind of the solution here is kind of like we touched on. First, make it work and make it right, then worry about making it fast. So first off, as make sure that the program actually works and it's giving you the correct answers. Then once you kind of have that baseline, then you can focus on making it faster. So the last one that I wanted to touch on is the not invented here syndrome, which is kind of the going back to the argument of reinventing the wheel or avoiding external solutions in favor of building custom in-house tools or frameworks rather than the external solutions, which are better. Now, one thing I do want to caveat here is this is not to say that you should never build your own X, Y, or Z from scratch. Because, for example, building your own web server is one heck of a good learning experience. Or, same thing with building your own kernel or building your own operating system or things like this. Yes, the pre-built versions have been battle tested and are going to be better, but that doesn't mean you can't try to roll your own in order to gain a better understanding of how these things work. Because as we touched on, I don't remember what episode it was off the top of my head, but we did an episode talking about why writing your own HTTP server is a fantastic exercise in software development, but also in cybersecurity, especially if you're using a more low-level language like C or C++ that isn't memory safe. If you're playing the drinking game of every time I talk about C and C++ not being memory safe, there you go again. But if you're using a language like that, you really have to take into account of you're dealing with a bunch of user input and undefined strings of various lengths. And even if you're not using a language like C or C++, there still is a bunch of variability in the types of requests and garbage that you might get from an HTTP request that you have to account for, and all the various potential attack vectors that a threat actor might do when trying to attack an HTTP server. So it is a fantastic exercise to go through, but that's not to say that if you want to, create a website for yourself that you should build the web server from scratch. There are plenty of good solutions out there like Nginx and Apache that are battle tested and used all over the place, that are probably what you should be using rather than, rolling your own. And so kind of some other symptoms of this is, rebuilding functionality that's already established in libraries or tools that are already provided. And, I understand from the aspect of, wanting to do everything yourself because as you all know, I'm writing my own video game from scratch. Is that the best solution? Absolutely not. Should I be using some kind of game engine that makes developing this a heck of a lot easier? Almost certainly. But the point of this is not to, the whole point of it is, a enjoyment for my own, personal enjoyment, right? I'm doing this because I want to. I'm not doing this because I'm trying to make the most polished AAA game ever. I'm doing this just as a fun side hobby project, and I want to, be able to do as much of it by myself as I possibly can, So the whole goal of it is kind of a learning experience and to better myself as a software developer and not rely on third-party solutions where possible. Now, I have touched on why I'm using a graphics library because mind you, when I first started on my video game, I was fully prepared to write my own graphics engine. And then I realized that was basically a full-on project equal to the size of making a video game. And I was like, okay, I'll just use an off-the-shelf one. Thank you very much. But basically everything else in it I've been trying to do as much as I can by myself, mainly because that's kind of what I set out to for this project. Now, if I was actually making this, as part of a company, or I was designing this as for an actual something that wasn't just a hobby personal project, then absolutely I would be using things like game engines and other developer tools in order to ease and make, the developing of the various graphical scenes and things a heck of a lot easier rather than doing it all by hand, writing all the code by hand. So, the obvious consequences here of this, not invented here thing is reinventing the wheel and wasting a bunch of time for potentially subpar results when there's already an off-the-shelf project or library or thing that already does what you're trying to do. And the other aspect to it also is if you create your own version, you are then in charge of maintaining that version. So unlike if you're pulling, some open source repo for, like in my case, I'm using Raylib for the graphics library. If I was the one writing my own graphics library, anytime there was a bug, issue, vulnerability, things like that, I would be the one required to fix those and maintain those. But because I'm using one that's already pre-built, I don't have to worry about that. So you kind of shift that burden over to someone else. Now, depending, you can make the counter argument that, well, if I shift the burden over to someone else and things don't get done the way I want them to, then I'm kind of out of luck. And yes, that is, I guess, a trade-off you have to make. But depending on what this thing you're trying to reinvent is, I mean, is it worth, having all of the extra staff and all the time and effort and all that stuff to maintain said product when it's already being maintained by someone else where their sole focus and, responsibility is working on that one thing and making it the best that they can be? Up to you. So yeah, one of the, I guess, another example of one of these reinventing the wheel when you shouldn't is some kind of OAuth authentication service or system. Now, can you roll your own? You absolutely can. Should you? Probably not. Another thing, like we touched on, web servers is another one. So when it comes to how do you fix this, I think the biggest thing you have to look at is you have to understand what your problem is and evaluate any existing solutions that exist on the market. And are you okay, committing to using one of those, or is the development effort small enough that you're okay with committing those resources to building everything yourself and maintaining it? Because granted, there might be some tools and libraries out there that are fairly basic, and rather than adding those additional dependencies, you're okay with, building your own tools from scratch. Now, again, there might be other instances where there's some kind of unique use case that someone has already developed a solution for, and that then saves you all the headache and effort of trying to reinvent the wheel, so you go ahead and pull that in. So really, there is no kind of silver bullet solution here. You really just have to understand the root of the problem and evaluate your potential alternatives in order to understand, okay, so I'm trying to do types of encryption. Should I write my own encryption algorithms, or should I use one that's already been tested and bulletproof and like OpenSSL? I think the answer is pretty obvious on which one you should use, but I will let you answer that question for yourself. But yeah, so being able to understand what your use case for potentially looking to build your own tools are, analyzing if there are tools that already exist, seeing what their capabilities are, seeing what their limitations are there competitors to that one? What are their capabilities and limitations? Maybe you give some kind of level of effort estimate of how much it would cost to essentially build all that in-house and maintain it, and kind of weigh those pros and cons and options before you go ahead and just blindly say, we need to build everything in-house. Now, with that being said, though, like I said, if you're trying to do it for a learning opportunity, building everything yourself can be insanely rewarding. Is it a lot of work? Absolutely it is. But it is a very rewarding experience. But again, it's not something you should be doing just because you want that rewarding experience, especially, if you have things like deadlines and all that good stuff and resources that you have to manage. If basically everything outside of it being a pure hobby project, you really need to evaluate and take a look at solutions that already exist before you say we're going to build everything ourselves. That one is a little more, I think, ambiguous than some of the other ones. A lot of the other ones, like the premature optimization, that kind of has some pretty easy solutions for it. Same thing with the cult programming, making sure you kind of understand the code that you're copying around rather than just blindly doing it. Spaghetti code and the God object, again, there's kind of easy to define problems and solutions there, but the one with the wanting to build everything in-house and making custom tooling is a lot more ambiguous, because it's a lot more kind of a case by case rather than okay, here's a prime example of it, that kind of a thing. Those are some of kind of the main anti-patterns that generally crop up fairly consistently in software development, and some of the ways that you can avoid them. But before we conclude this episode, I think we should get back to our trivia question. Speaking of which, this week's trivia question has to do with email, and that is another one that you probably shouldn't be rolling your own email solution. There are plenty of them out there, and it's probably better to use one that already exists rather than rolling your own. So I guess there's another example of that. But getting back to the trivia question, which protocol is used to send emails over the internet? Now, again, I will accept either the acronym or the actual name. So if you said SMTP or Simple Mail Transfer Protocol, congratulations, you got this week's trivia question correct. And if you enjoyed this episode, definitely be sure to leave it a rating and review and subscribe if you haven't done so already. And also be sure to share it around with a friend or family member. And if you have any questions about this episode or have any topics, ideas for future episodes, definitely be sure to shoot me an email at contact@darkassassinsinc.com. The link for that is down in the show notes. But also, if you're on YouTube, you can just leave a comment down below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.